Hello dear friends, I am Professor D.G. Trivedi going to take your next lecture regarding flip-flops. We have started that flip-flop is a memory element. It is a 1-bit memory element. Flip-flop is an electronic bistable device which is having two outputs Q and Q bar which are complements to each other, and it is a 1-bit memory device. This kind of things we have studied. We have studied the basic RS flip-flop. That means there are two inputs R and S, and there are two outputs Q and Q bar. If S is equal to 0, R is equal to 0, no change conditions, that means output is not going to be affected and output retain the last value. That means if the Q is going to be 0, it remains to be 0. If Q is going to be 1, then output remains to be 1. So this is called your basic RS flip-flop. Then there is a set conditions. S is equal to 1, R is equal to 0. The flip-flop is going to be set. That means Q becomes 1 and Q bar becomes 0. Then there is a reset conditions. That is R is equal to 1, S is equal to 0. Flip-flop is going to be reset. That means Q becomes 0 and Q bar becomes 1. Then the last conditions is a forbidden conditions. That is R is equal to 1, S is equal to 1. Both the outputs will be in the same state, Q is equal to Q bar. Hence, in a truth table, output is going to be question mark. That means it is a forbidden conditions and it is decided not to impose these conditions. Now, using a NAND gate and NOR gate, this two type of basic RS flip-flop was prepared. And both this basic RS flip-flop is having a same symbol and same truth table, as we have seen in a previous topic. So we are starting now the advance of this flip-flop, and that is called gated flip-flop or clock RS flip-flop. Two different methods for constructing an RF flip-flop were discussed in section 8.1. The NOR gate realization in figure 8.3b is exact equivalent to the NAND gate realization in the figure 8.8a, and they both have exact same symbol and same truth table as given in figure 8.6. So we have discussed the truth table. R is equal to 0, S is equal to 0, no change conditions, or output remains in the last state. Set conditions, S is equal to 1, R is equal to 0, Q is going to be 1, Q bar is going to be 0, that is called set conditions. Then reset conditions, S is equal to 0, R is equal to 1, that is reset conditions, Q is going to be 0, and S and R is going to be 1 conditions, that is forbidden conditions. So this is the truth table that we have discussed. Now, what is happening in this flip-flop? What is the drawback of this flip-flop? What is the limitation of this flip-flops? Rather, we can say that drawback, other limitations. That is, as soon as you change the input, that means from the set condition to the reset condition, output is responding to that input condition immediately. That means if the flip-flop is set and you apply the reset conditions, and flip-flop will change the output immediately, or it is responding to the input conditions immediately. Only it will retain the informations when R is equal to 0, S is equal to 0, that retains the information, that will store the information only. That means we cannot change the input conditions without affecting the output. This is the main limitation of basic RS flip-flops. So this basic RS flip-flop is clocked, or it is going to be enable or disable using some signals. This kind of flip-flop is known as a gated flip-flop, or it is called clock RS flip-flop. To prepare this kind of clock RS flip-flop, two additional AND gates at the inputs at R and S is connected, and one of the input of both the AND gates are shorted, and there is a clock input, or it is called enable input, is connected. and other two inputs of the AND gates are working as the R and S inputs. Both the RS flip-flop or latches are said to be transparent. That is, any change in input information at R or S is transmitted immediately to the output at Q and Q bar according to the truth table. So what we have discussed, that is immediately output is responding to the input conditions. That's why this flip-flop is said to be transparent. Transparent means the output is responding to the input conditions immediately. Input changes, output is also changes accordingly. It doesn't retain that information unless it is going to be 0 0. That's why it is called a transparent flip-flop. So RS flip-flop, basic RS flip-flop is a transparent flip-flop. Remember these words. Now the clock RS flip-flop. The addition of two AND gates at the R and S input as shown in the figure 8.11 will result in a flip-flop that can be enable or it can be disable. When the enable input is low, the AND gate output must both be low and changes in neither R nor S will have any effect on the flip-flop output Q. The latch is said to be disabled. When the enable input is high, the information at the R and S input will be transmitted directly to the output. The latch is said to be enabled. So you can see that this is the symbol of basic RS flip-flop, where there are two inputs S and R, Q and Q bar. This is a basic RS flip-flop, can be prepared either from the NOR gate or can be prepared from the NAND gate. And prior to this, at the input, there are two AND gates are introduced. These two AND gates, one of the inputs of both the AND gates are shorted or it is connected and it is given as enable inputs. And other input is working as a S input and this is going to be R input. Now we have the three inputs, S, enable input and R. So this symbol of basic RS flip-flop is converted to this symbol S, enable input and R. There are three lines and there are two outputs Q and QR. Now you can see that if S is equal to 0, R is equal to 0, again the output of this AND gate is going to be 0 because output of the AND gate is going to be 0 whenever any one of the input is going to be 0. That is the reasons S is equal to 0, R is equal to 0 for the basic RS flip-flop, which is a no change conditions, it retains into the last state, that is Qn. Like the previous state or Qn it will be there. That is called no change conditions or it retains in the last state conditions. Even if the enable input is going to be high. When enable input is going to be high, whatever changes at the S and R, that will be reflected to the actual input of S and R of basic RS flip-flop and the flip-flop will respond to that inputs. If enable input is going to be high, then S is equal to 1, R is equal to 0. That means output of this upper AND gate is going to be 1 and output of the lower AND gate is going to be 0. So S is going to be 1, R is going to be 0. That means it is a set condition for the basic RS flip-flop and the flip-flop is going to be set, Q becomes 1 and Q bar becomes 0. If you apply the reset condition, that is S is going to be 0, R is going to be 1, output of the upper AND gate is going to be 0, output of the lower AND gate is going to be 1 because enable is going to be high and hence the flip-flop is going to be reset. That means as long as the enable input is going to be high, the flip-flop is going to be responding to the S and R inputs. Now what happens if the enable input is going to be low? If this enable input is going to be low, one of the input of upper AND gate as well as lower AND gate is going to be low. So both the AND gates output is going to be low. That means S is going to be 0, R is going to be 0. No change conditions. You can say that and flip-flop is going to be latch into the last state. That means when the enable input is going to be high, flip-flop is responding to that inputs S and R. But when the enable input is going to be low, flip-flop is disabled. And you can change the input S and R without affecting output Q. This is the way the flip-flop, basic RS flip-flop is enable or disable using these two AND gates. Or it is called clock flip-flop. That means when the clock is going to be high, the flip-flop is going to be enabled, or it is responding to the S and R input, set or reset. So depending upon the set conditions, the flip-flop is going to be set. That means it will store the output 1. And when you give the reset conditions, then the flip-flop is going to be reset and it will store the output 0. So this way, the flip-flop can be enabled or disabled using these two AND gates. And that's why it is called the gated flip-flop, or it is known as a clock RS flip-flop. So when enable is equal to 0, the flip-flop is disabled and R and S have no effect. Thus the truth table entry for R and S is to be X. Don't care. So you can see the last conditions of the truth table. When the enable input is going to be low, flip-flop is not responding to the SNR. SNR may be anything. Either it is going to be 0 or 1. The output does not change, or output is going to be latched into the last state. So it remains into the Qn. You can say that. Qn plus 1 is the next state, and Qn is going to be the last state. You can say that. The output will change in response to the input changes as long as the enable is going to be high. When the enable input goes low, the output will retain the information that was present on the input when the high to low transition takes place. In this fashion, it is possible to stop or clock the flip-flop in order to store the information, set it or reset it at any time, and then hold the stored information for any desired period of time. This flip-flop is called a gated or clock RS flip-flop. The proper symbol and truth table are given in figure 8.11b. Notice that there are now three inputs: R, S, and the enable or clock input, which is labeled as EN. Notice also that the truth table output is not simply Q, but it is designated Qn plus 1. This is because we must consider two different instants in time. The time before the enable goes low, Qn, and the time just after enable goes low, that is Qn plus 1. When enable is going to be 0, the flip-flop is disabled and R and S have no effect. Thus the truth table entry for R and S is equal to X. That is called don't care. Now we will take one example, or that is related with this one, that is nothing but the explanation of Qn and Qn plus 1. Explain the meaning of Qn in the truth table. Figure 8.11b. Solutions. For the flip-flop to operate properly, there must be a positive transition on an EN input. That means the AND gate EN input must go high, then and only the sample data from S and R will be taken out of the AND gate. The gate is going to be open for a moment, and whatever input data was there at present at S and R will be directly passed through that, and it is available to the basic RS flip-flop. When enable is high, the information on R and S causes the latch to set or reset. Then, when the enable transition back to low, this information is retained in the latch. That means when the enable input becomes low, now what happens? The output of both the AND gate is going to be 0, 0. And hence, R and S input of the basic RS flip-flop is going to be 0, 0, no change conditions, whatever data was stored, last value of the data which was stored, either it was set or it was reset. It remains there, or it is going to be stored and hold that information for any desired period of time. When this negative transition occurred, both R and S inputs were low, 0, and thus there was no change of the state. In other words, the value of Q at time n plus 1 is the same as it was at time n. Remember that the time n occurs just before the negative transition of En or clock pulse, and time n plus 1 occurs just after the transition. So at the time in the truth table Qn plus 1 is the next data after the clock pulse is gone. That means the negative transition has taken place. And Qn is just before the negative transition take place. This is two different realizations of clock RS block using NAND gate as well as NOR gate. You have seen in the NAND gate how basic RS flip-flop was there. There are two NAND gate was here. Output is Q and QR. Both the output is crossover and given as input to the NAND gate. And prior to that, there was the NOT gate was there. Now, prior to that NOT gate, if there is an AND gate is put over here, that means AND gate plus NOT gate, it becomes an NAND gate. So, this also becomes NAND gate as well as this also becomes NAND gate because here also there is a AND gate which is followed by NOT gate, it becomes NAND gate. So, only using the four NAND gates like this, you can prepare a clock RS flip-flop or gated RS flip-flop using four AND gates only, which can be accompanied by a single IC 7400, which contains quad two inputs NAND gate. So using that IC, you can prepare this clock RS flip-flop. Similarly, this is using the NOR gate. Here, there are two NOR gates, and we have seen the difference between these two. Now, to make the symmetrical, S is in upside and R is going to be in downside, this inputs are inverted or it is going to be crossover. And R is made here, S is made here. Now, here there are two AND gates is going to be introduced. And this way, using the NOR gate and AND gate, you can prepare a clock RS flip-flop which is having similar truth tables will be there and similar symbols will be there. So this is the two different realization for the clock RS flip-flop. The logic diagram shown in figure 8.12a and b illustrate two different methods for realizing a clock RS flip-flop. Both realizations are widely used in medium and large scale integrated circuits, and you will find them easy to recognize. So this kind of clock RS flip-flop are available in so many medium scale and large scale integrated circuit IC forms. So in a TTL as well as in CMOS, such kind of circuits are already built in and IC form, and it is available. You can directly utilize S enable and R is going to be input, Q and Q bar will be output in IC forms. Now, and to understand this clock RS flip-flop, we are going to take one examples in the form of waveforms. So there are three inputs waveforms are given. Consider that S is going to be given as a waveforms, R is also given as a waveforms, and enable input is given as a clock waveforms like this. So enable input is sometimes when it is going to be low, it is shown by 0. When it is going to be high, it is shown by 1. Similarly for R and S. And you are asked to sketch the output waveform for this one. So this example is this. In figure 8.13 shows the input waveform R, S and enable applied to the clock RS flip-flop. Explain the output waveform Q. Now, initial condition, mostly if it is not given, always take that output is in a reset condition. That means output has stored in a 0 prior to the time t1. So prior to the time t1, enable is going to be low. Enable is going to be low. That means whatever R or X S may be, right? That means R or S may be anything. It remains into the last state. And last state, that means initial state, we will consider that Q is going to be 0 and Q bar is going to be 1. So flip-flop is already reset. So initially the flip-flop is reset. Q is going to be 0. That we are taking. Now at the time t1, this is the stop time. Timeline is shown here. So at the stop time t1, the enable becomes high. As soon as enable is going to be high, flip-flop is responding or it becomes transparent for the input conditions. So whatever input condition is present, that will pass over that and it will affect the flip-flop outputs. So what is R is equal to? R is equal to 0, S is equal to 1, that means set condition. So at the start time T1, the flip-flop is going to be set, so flip-flop output Q, which was 0, is going to be set and it becomes 1. Now, between T1 and T2, the input R and S is not going to be changing. And hence, at T2, again the enable becomes low. That means when the enable input becomes low, from high to low, it will retain the last value of the Q. The last value of the Q was 1, so it will remain to be 1 until time T3 because enable is going to be low. So it is not responding to the change in the inputs R and S, which is changing in between. But the flip-flop is not going to be responding as long as the enable input is to be low, or that we can say that flip-flop is disabled. Now between the time T3 and T6, again the enable is going to be high. When the enable is going to be high, it is going to be responding according to the input conditions. Whatever the input condition is there, it is responding to that, or the flip-flop is going to be enable. So we can consider that at time T3, when the flip-flop is going to be enabled, the R is going to be 1 and S is going to be 0, so the flip-flop is going to be reset and output Q becomes 0 or it is going to be storing 0. So it is reset from 1 to 0. Again at the start time T4, it is responding to the input conditions. That is R is going to be 0 and S is going to be 1, so the flip-flop is going to be again set at the start time T4. At the start time T5, R is going to be 0, S is going to be 0, that means no change condition. So even if the enable input is going to be high, the R is going to be 0, S is going to be 0, that is no change conditions, and output will retain the last value of the Q. And that last state was 1, so it remains to be 1 at the start time T5. At the start time T6, what happens? The enable input is changing from high to low, or negative transition will take place from the stop time. At that time, whatever the last value of Q was there, that will be stored or it is going to be retained. So Qn and Qn plus 1 becomes same. So Qn was 1, so the flip-flop is going to be set and it will remain to be set at the stop time T6. Between time T6 and T7, the enable input is low. So that means the flip-flop is disabled. So in between, there is a change in the inputs R and S, but it is not responding to this inputs and it will remain to be disabled, or the R and S is going to be don't care, output is going to be retained to the last value of Q. And the flip-flop was already set, it remains to be set in between the time T6 to T7. Now, again at the start time T7, the flip-flop is enabled. From T7 to T8, the flip-flop remains to be enabled. But at that time, the R is going to be 0, S is going to be 0, so no change condition. So flip-flop is not going to be changing its output. And Q was 1, it remains to be 1. And that's why Q remains to be set only in between T7 and T8. After T8, the enable input is going to be low, so it will retain that information for any desired period of time until again the enable input is going to be high, and if there is a reset condition is going to be there. So now we'll read that solutions which is written over here. Initially, the flip-flop is reset, Q is going to be 0. At time T1, enable goes high. The flip-flop is now enabled, and it is immediately set Q is going to be 1. Since R is going to be 0 and S is going to be 1, at time T2, enable goes low and the flip-flop is disabled. And the latch is in the stable state, Q is going to be 1. Between T2 and T3, both R and S changes the state. But since enable is low, the flip-flop is still disabled and Q remains at 1. Between T3 and T6, The flip-flop will respond to any change in R and S since enable is high. Thus, at T3, Q goes low because the reset condition is already there, and at T4, it goes high because of set conditions. No change occurs at T5 because of the 0, 0 conditions. At T6, the value of Q is going to be 1 is less, and no change in Q occurs between T7 and T8, even though both R and S are going to be changes because enable input is low. Between T7 and T8, no change in the Q occurs since both R and S are going to be low. Clock D flip-flop. Now, what are the limitations in this flip-flop? Clock RS flip-flop or gated RS flip-flop? The limitation was this. We require two data generator to set it or reset it. To store the output 1, to store the binary data 1, we have to give the set conditions. That means the data generator S is equal to 1 and R is equal to 0 should be applied. And there is an enable input should be given. To store a 0 in the output or to reset the flip-flop, you have to give S is equal to 0 and R is equal to 1. You have to apply it and you have to give the enable input high. These two different data generators is required in a clock RS flip-flop. This is one of the limitations. This limitation can be overcome in a clock D flip-flop. Moreover, in a clock RS flip-flop or a basic RS flip-flop, there is a forbidden condition. That means if R is equal to 1, S is equal to 1, the output is unpredictable. In a truth table entry, there is a question mark. That means both the output will be in the same state. Now, as soon as the input is going to be changed to 0, 0, which output is going to be 1 and which output is going to be 0, we cannot predict. That means it is a forbidden condition. So, there is a possibility of the forbidden conditions in a clock RS flip-flop. These two drawbacks or these two limitations can taken care in type of D flip-flop. D flip-flop is a modified version of clock RS flip-flop, you can say that. Instead of two data generator, because we know that RS should be complement to each other to set it or to reset it. And hence, between R and S, if we introduce one inverter or a NOT gate, that will take a single data generator only. And there cannot be a forbidden condition. That means R and S cannot be 1-1 conditions. That cannot be possible. So both these limitations can be taken care if we introduce a NOT gate between R and S, and that way this clock RS flip-flop is modified to D flip-flop or clock D flip-flop. So we are learning now the clock D flip-flops. The RS flip-flop has two data inputs, R and S. To store a high bit, that is 1, you need a high S, and to store a low bit, you need a high R. Generation of two data signals to drive a flip-flop is a disadvantage in many applications. Furthermore, the forbidden conditions of both R and S high may occur inadvertently. This has led to the D flip-flop, a circuit that needs only one single data inputs. Figure 8.14 shows a simple way to build a D data flip-flop. D means data flip-flop. This flip-flop is disabled when enable is going to be low, but is transparent when the enable is going to be high, just like in clock RS flip-flop. The action of the circuit is straightforward and follow. When enable is low, both the AND gates are disabled. Therefore, D can change the value without affecting the value of Q. On the other hand, when the enable is going to be high, both the AND gates are enabled. In this case, Q is forced to equal the value of D. When the enable again goes low, Q retains or stores the last value of the D. Now we'll see the circuitry here.
So you can see that this is your basic RS flip-flops,
Which is having two input S and R
and it is having
two
two
outputs
outputs
Q
Q
and
and
Q
Q
bar
bar,
which are supposed to be complement to each other.
Prior to that, if there are two AND gates are going to be introduced and two AND gates, one of the inputs are shorted and it is called a enable inputs.
That way, this is your clock RS flip-flops.
Now, here it was S and here there was R input was there.
Between these two, there is one more inverter is to be placed at the input side. And that way, clock RS flip-flop is converted into the D flip-flop, and this S input is designated as a D input. Now what happens?
If enable input is going to be low, one of the input of both the AND gate is going to be 0, 0. And hence the output of this both the AND gate is going to be 0, 0. That means S is going to be 0, R is going to be 0, no change conditions. The flip-flop
Retain the last value, whatever the previous value was stored, it will be not changing. And the flip-flop is said to be this.
So whenever enable input is going to be low, you can change this data inputs. And this data inputs, if it is going to be 0, you can make it 1, or if it is 1, you can make it 0, but it will not affect the flip-flop output. Output retains last value. So you can change the input value D without affecting the output value of the flip-flops. Now, when the enable input is going to be high, if D is going to be 1, the output of the upper AND gate is going to be high and output of the lower AND gate is going to be low, and hence it is a set condition and the flip-flop is going to be set. Q will take the value of D. That means Q becomes equal to value of D. D was 1, so the Q becomes 1, or it is going to be set when the enable input is going to be high. If D is going to be 0, then this gate is getting 0 input, and this gate, because it is inverted, it is getting 1. So here there is a 1 1 condition, so R becomes 1, S is going to be 0, reset condition for the flip-flop, and Q takes the value of D, that is going to be 0. So Q is equal to 0 or Q is equal to D will be there. So as long as enable input is going to be high, whatever you changes at the input D, that is directly transparent or transferred to the output of the flip-flop. So output of the flip-flop Q will take the value of D
as long as enable input is going to be high.
and after that, when enable goes low, the last value of the D, which is going to be stored there, and thereafter, until the enable is going to be high, you can change the input of D and output is not going to be changed. It will be retained or it will store that information for any desired period of time. There are many ways to design a D flip-flop. In general, a D flip-flop is a bistable circuit whose D input is transferred to the output where enable is going to be high. Figure 8.15 shows the logic symbols used for any type of the D flip-flop. In this section, we are talking about the kind of D flip-flop in which Q can follow the value of D, while enable is going to be high. In other words, if the data bit changes while enable is going to be high, the last value of D before enable returns low is the value of D that is going to be stored. This kind of D flip-flop is often called a D latch. So the IEEE symbol for the D latch is going to be this. There are two inputs. One of the input is data input D. This is going to be enable input. Both IEEE symbols, both the inputs are written inside this box, DN, EN, and outputs, which is given by this line, and with the bubbles this line, Q and Q bar will be there, which is written outside the box for IEEE symbols. But for the logic symbol, all input and outputs which are written inside the box only. This is the difference between IEEE symbol and logic symbol, remember. But this is the logic symbol and IEEE symbol for D type of flip-flops. This is the truth table for D type of the flip-flop. So, when the enable input is going to be low, that means both the AND gates are going to be disabled, flip-flop is disabled, and it will retain the last value. So, Qn plus 1 is nothing but the previous value of output, and that is going to be Qi. So it is not going to be affected. Whatever D value is going to be there, that output is not going to be affected because of that. You can change the value of D without affecting the output of D flip-flop whenever the enable input is going to be low. And when the enable input is going to be high, Q takes the value of D. That means if D input is going to be 0, the output Q1 plus 1 is going to be 0 because enable input is going to be high. It will respond to the input. And when the D input is going to be 1, output is going to be 1. So this way it is responding to this inputs. Figure 8.15b shows the truth table for a D ledge. When the enable is high, Q takes on the last value of the D. If D is changing while enable is high, it is the last value of D that is going to be stored. The idea of data storage is illustrated in figure 8.16. The idea of data storage is illustrated in figure 8.16. 4D latches are driven by the same clock signals. When the clock goes high, the input data is loaded into the flip-flops and appear at the output. Then, when the clock goes low, the output retains the data. For instance, suppose there are data inputs is D3, D2, D1, D0 is going to be 0, 1, 1, 1. When the clock goes high or enable goes high, it will take the value of this one. And Q3, Q2, Q1, Q0 takes the value of this one. That means it becomes equal to 0, 1, 1, 1. This is the way the storing a 4-bit word is going to be there, river. This is 4D latch is going to be there. Here it is designated, this D input is designated D3, this D input is designated D2, D1 and D0. So here you have given the data is going to be 0, 1, 1, 1. Now when enable input is going to be high, this data is transferred to the output and Q3 becomes 0, Q2 becomes 1, Q1 becomes 1 and Q0 becomes 1. That means data D3, D2, D1, D0, whatever the data was there, when the clock is going to be high, that data is going to transfer at the output, and then after, when the clock becomes low, that data is going to be retained or it is going to be stored. And that way, it can work as a data storing device for the nibble. Now, if you are utilizing this kind of 4-bit D flip-flop, a number of sets like this one, which is available in the IC 7475, you can utilize more than one IC. You can have 8-bit data can be stored. You can have a 16-bit data can be stored like that way. After the clock goes low, the output data is retained or stored. As long as the clock is low, the D values can change without affecting the value of Qs. The IC 7475 in figure 8.17 is a TTL MSI circuit that contains 4 D latches. It is called a quad bistable latches. The IC 7475 is ideal for handling a 4-bit nibbles of the data. If more than one 7475 is used, word of any length can be stored. This is the way the IC 7475, this is TTL IC set. That means you require a VCC voltage of 5 volt, which should be given on pin number 5. Pin number 12 is the ground. So this is the supply, 5 volt regulated power supply is given to this IC. This IC contains 4 D latches, which we have seen in previous circuitry, which can be designated D0, that is going to be LSB, D1, D2 and D3. D3 is going to be MSB. So this is a 4-bit nibble data is going to be there. You can see that with each flip-flop, Q, Q0 and Q bar, Q1 and Q1 bar, Q2 and Q2 bar, Q3 and Q3 bar, this all are given. And there are two enable inputs, that is enable input 1 and enable input 2. Thus both enable input can be shorted and you can have a combined one enable input or clock input like this one. This circuitry is more explanatory or with the logic circuit diagram is shown here. That means it is having two output Q and Q bar. D input for each flip-flop, and there is a enable inputs. So this way, this IC 7475 contains 4 D latches, and hence it can handle 4-bit data, that is nibble can be handled. Thank you very much, friends. So this way we have studied here the gated clock RS flip-flop and or gated or clock D flip-flop, data flip-flops. Thank you very much, friends.